Hello everyone. This presentation is going to talk about equal area and Stekly criteria, which are two critical criterions in cryostability of superconductor. First of all, let's take a look of today's presentation content. In order to help us understanding equal area and Stekly criteria, we will start with some basic equations and definitions in cryostability, like power density equation, matrix current density, total joule dissipation, and time-dependent boiling heat transfer. Then we will introduce Stekly criterion and equal area criterion individually. At the beginning, here is a power density equation governing the temperature of a unit superconductor volume, considering of thermal stability of a superconducting magnet carrying operating current. The left-hand side represents the time rate of change of thermal energy density of the conductor, where capital C is the heat capacity per unit volume of the conductor. For complete the steady-state stability, this term must remain zero at all times. In the right-hand side, the first term describes thermal conduction into the superconductor, and the last term represents cooling, where detailed parameters will be introduced in next slide. The second term is joule heating, and the third term describes non-joule heat generation, named as disturbance. In order to keep left-hand side equal to zero, we have to balance the right-hand side terms. Secondly, let's introduce the concept of matrix current density. As we already know, a superconducting wire is a composite of superconductor and matrix. The figure on the right is an image showing the state of immersing the superconducting wire in the coolant. In most applications where cryostability is applied, we must assume that the conductor may operate in the fully normal state. The joule heating per unit length will be equal to the cooling flux per unit length as shown in equation below, with PD as the total conductor perimeter. The constant Fp quantifies the fraction of PD exposed to cryogen. If we consider normal state, that current will all flow through the matrix. Therefore, the left equation will be rho multiple matrix cross-section multiply square of current density. Finally, we can get the equation of matrix current density. Thirdly, about the joule heating of superconductors. Due to the existence of the current sharing phenomenon, the superconducting wire does not have zero heat dissipation at the critical temperature. First of all, we assume that our superconductor is ideal, that is, as shown in the lower right figure, the resistance is absolutely zero when it is less than the critical temperature. At this time, we also know that due to the existence of the matrix, we generally use the two-fluid model to represent the superconducting wire, in which the resistance of the matrix is ρ, which is much smaller than the resistance value of the superconductor under normal conditions. Next, we assume that the critical current is linear with temperature and that the critical current at the critical temperature of current sharing is IT. The total joule dissipation is simply the square of the current through the substrate multiplied by the resistance of the substrate. The current through the substrate is equal to the value of the shared current minus the critical current of the superconductor. After bringing the above formula into it, we can finally get the formula in the pink frame. When the temperature is lower than the critical temperature of current sharing, no current passes through the substrate and no heat is generated. Between the critical temperature of current sharing and the critical temperature of superconductor, as the temperature increases, the current flowing through the substrate gradually increases. When the temperature is greater than the critical temperature of superconducting temperature, the joule heat dissipation of the superconducting wire is equal to the resistance of the substrate multiplied by the square of the critical current at the critical temperature of the current sharing. Finally, temperature-dependent boiling heat transfer refers to the process of heat transfer when the liquid contacts a high-temperature surface during the heating process because the surface temperature exceeds the saturation temperature of the liquid and boils. In temperature-dependent boiling heat transfer, the heat transfer rate is closely related to the temperature difference between the liquid and the surface, and the greater the temperature difference, the higher the heat transfer rate. Because the larger the temperature difference, the speed at which the liquid evaporates rapidly to form bubbles on the high-temperature surface may increase, thereby increasing the heat transfer rate. However, when the temperature difference between the liquid and the surface reaches a certain level, a protective film of vapor will form between the liquid and the surface, thereby reducing the heat transfer rate. As shown in the figure, when the temperature difference is close, the heat transfer rate increases with the increase of the temperature difference. Then when the temperature difference reaches a certain value, the contact area is reduced because the bubble production rate is too fast. So the heat transfer rate decreases until the vapor protective film is formed. Then the heat transfer rate increases gradually with the increase of temperature difference. Next, let us introduce what is the Stekly criterion. Let's look back at the power density equation introduced at the beginning, and the left side is known to be 0. Stekly assumes that thermal conduction and non-Joule heat generation are 0, near equilibrium Joule heat and convective cooling. Here, Stekly focuses on local heat dissipation to ensure that no localized phase transition occurs in the superconductor. Import the total Joule dissipation formula we derived before, and we know that Joule heat can also be calculated by matrix current density. In the calculation formula of matrix current density, minimum heat flux is equal to heat transfer coefficient multiplied by the temperature difference. The cooling in the Stekly standard is always greater than the Joule heat, so finally we can get the inequality in the pink box. Let's look at Stekly's criterion with temperature-dependent boiling heat transfer. First, from the total Joule dissipation equation, we can derive the Joule dissipation density and its derivatives through the steady-state low-temperature stability. Here, if we assume that IT is equal to the critical current at the operating temperature, we will have a solid line in the graph below. Stekly's criterion assumes that the derivative of the Joule dissipation density should not be greater than the time-dependent heat of boiling transfer at any temperature. In addition, in actual conditions, the critical current under equal flow should be smaller than the critical current under operating temperature. Therefore, the derivative value of the actual Joule dissipation density is small, and the superconductor is considered stable and safe. In equal area criterion, unlike Stekly criterion, that conduction is no longer 0. The thermal conduction along the conductor axis aids the local cooling to remove the Joule dissipation. Thus, the equal area criterion works only when Joule dissipation is not spread globally over the entire winding. The principle of equal area criterion states that, on the cross-line area bounded by the boiling heat transfer larger than Joule dissipation density and Joule heat dissipation curve, is equal to the other cross-line area bounded by the Joule heat dissipation larger than boiling heat transfer and boiling heat transfer curve. In conclusion, first, the power density equation is a key equation for stability that the concepts for stability have evolved around solutions to simplifications of it. Second, boiling heat transfer is a variable that depends on the temperature differential between the coolant and the target. Third, Stekly criterion assume no thermal conduction and non-Joule heat generation. It requires Joule dissipation density should always smaller than boiling heat flux. Last, equal area criterion considered thermal conduction term. It allows the Joule dissipation density curve to be intersected with the boiling heat flux curve. However, the area before and after intersection should be equal. Thank you for your listening.